we have a typical Statistics 1 hypothesis testing question of moderate difficulty. How large would an observed mean have to be significantly more than 1/2 based upon a random sample of 8 observations, a population standard deviation of 3/4, and an alpha, that's the significance level, of 5%. And the question asks us to round the final answer to the nearest thousandth. So that is 3 decimal places. So let's start with this observed mean. This is what we want. And that is X bar. That's what we want. And we want it to be significantly more than 1/2. We want to know what value should we observe to be significantly more than 1/2. Significantly more is specifying our alternative hypothesis. So we're going to write that first. So I'm writing the alternative hypothesis, H1, and some of your professors may use HA, doesn't matter, obviously. But the alternative hypothesis is that the population mean, which we symbolize by the Greek letter mu, is greater than 1/2. That's the word significantly is what tells us that we're specifying the alternative and not the null hypothesis. But of course, the null hypothesis would be that the population mean, mu, is equal to 0.5, 1/2. So that's really your first step in dealing with this, is knowing your null from your alternative hypothesis. Now, it also says based on a random sample of 8 observations. So, of course, n is equal to 8. I'm going to write that down. And it says a population standard deviation. Now, you should ask yourself, what is the symbol for population standard deviation? And you should know that that's the lowercase Greek letter sigma. And so this is 3/4. I'm going to write the 3/4 as 0.75 because it's just a little easier to enter into the calculator. And the alpha, the significance level, is 5%. So I'm going to write the Greek letter alpha equals 5%. But I'm going to also write this as a decimal, which is 0.05. Because the table that we're going to use is going to look at alpha as a decimal. So now we have all the information. We don't even need the words anymore. And everything in hypothesis testing for the normal distribution with a known standard deviation comes out of one simple little formula. It's the standardization formula, which gives us our z-score. So I want to write that down. So z is equal to X bar minus mu naught. Naught, it's kind of like the English word for 0, but it comes from the idea of the null hypothesis. So we call this the hypothesized mean. And the reason we call this the hypothesized mean is that it is hypothesized, but under the null hypothesis. But I want to leave it as a symbol here because the algebra is easier with symbols than algebra is with numbers, you know? And this is divided by sigma sub X bar, which is called the standard error of the mean. And there's a formula for this. So I'm going to write it right here. So we have this thing called the standard error of the mean. I'll just write SEM. And we have sigma sub x bar is equal to sigma over the square root of n. So this sigma sub x bar is how some people read it, is also called the standard error of the mean. And this is equal to the standard deviation of the population divided by the square root of the sample size. So this is a formula you need to know. But I want to write it in this compact way because we have to do some algebra. And I don't want to do algebra with something annoying. I'd rather plug something annoying in at the end of the calculation and do the algebra with the most simple symbolic representation we can possibly have. And so that's what we're doing here so far. So this is the way that we standardize this. And what we need to know next is when we're going to reject the null hypothesis. So we reject the null hypothesis when the z observed is greater than or equal to the z sub alpha. Now, this is read z sub alpha. I'll write ZEE sub alpha. And I'll put it in quotes because this is how it's read. And I have a whole video on Z sub alpha. You could look that up. But this is also called the critical value. And I'm just going to write crit for critical value to save a little space. And this is not a 2, this is an alpha. And we already wrote down that alpha was equal to 5%. Okay. So this is what's called a right-tailed test because the alternative hypothesis says that the population mean is greater than, notice this points to the right, greater than 0.05. So it's called a right-tailed test. This inequality symbol points to the right. So for the visual learners, the little picture of this, not that it's not necessary, but if you want a little picture of this, not drawn to scale, nowhere near scale, I probably should have, but this is your alpha level, and this is 5%. And this area here is where we reject the null hypothesis. So for your visual people over there, this is where we reject the null hypothesis. Now, what is this value? This value is your Z sub alpha. And of course, we have a table for this. Okay? Now, this is not necessary. This is just helpful for visual people. But what's necessary is we're going to have to solve this equation for x bar. And well, it's not an equation, it's an inequality. But we have to solve this inequality for x bar. And if you're looking at this, you might say, well, where's the x bar? I don't see it. Well, we're going to substitute the formula into this, and you see there is an x bar. So what we're going to do is we're going to write this as x bar minus mu naught divided by sigma sub x bar is greater than or equal to z sub alpha, because it's a right-tailed test. This points to the right. And we'll look the z sub alpha up later. That'll be like the last thing we do when we plug in all the values. But right now we want to solve this equation, this inequality, for x bar. So we would multiply both sides of this inequality by sigma sub x bar, the standard error of the mean. And in so doing, we get to cancel out this sigma x bar over here. And so we are going to write this as x bar minus mu naught is greater than or equal to sigma sub x bar z sub alpha. Right, so we're almost there. We're solving for x bar. And we're almost there. Now, can you figure out what to do next? Well, if you said we're going to add mu naught, the hypothesized mean, to both members of the inequality, well, you'd be right. So we go plus mu naught, draw a little line the way we were taught in middle school, and we get x bar is greater than or equal to mu naught plus sigma sub x bar z sub alpha. Now we're almost there. All we have to do is plug in all the numbers and we'll get it. But let's look at what this says. This says, for this mean, for this sample mean, also known as an observed mean, for this sample mean to be statistically significantly greater than 1/2. Here's where the 1/2 is. It's the alternative hypothesis, greater than 1/2. For us to view this sample mean as being significantly greater than 1/2, this sample mean itself has to be greater than or equal to, at least, whatever the hypothesized mean is, which in this case is 1/2, times the standard error of the mean, which we have a formula for, times the critical value, which we are going to look up in a table. So what I'm going to do next is I'm going to write this in the middle of a nice new piece of paper, and I'll show you how to plug everything in. So I'm just writing this over. We have x bar is greater than or equal to mu naught, the hypothesized mean, plus sigma sub x bar, the standard error of the mean, times z sub alpha, the critical value. That's where we're starting. Now, mu naught is 1/2. Let's put it in. Right, we got that. And now we need sigma sub x bar, the standard error of the mean, and we have this nice little formula. Sigma sub x bar is equal to sigma, the population standard deviation, divided by the square root of the sample size. So this, now sigma is equal to 0.75, so let's put it in. Now let's look what the sample size is. N is equal to 8. So let's put it in. And now we have to look up z sub alpha. We need to know alpha. Alpha is equal to 0.5. So we have to go into some kind of book that has a table at the end. And here we just so happen to have a z sub alpha table. Now, z sub alpha, this critical value, is actually the z-score that gives alpha area to the right. So if we want 5% of the area to the right of this critical value, we look up 5%, which is 0.05. This is the alpha. This is the 0.05. And the z sub alpha is 1.645. So I'm going to write that down. 1.645. Now, if your professor doesn't give you a nice simple table like this and gives you percentiles instead, this is the 95th percentile because 100 minus 5 is 95. So this z sub alpha, z sub 0.05, is equal to the 95th percentile of the standard normal distribution. So if you have a percentile table, you look up the 95th percentile. Now we have to plug this into the formula. So, good thing I have my calculator. Now, type in 0.5 plus, and now we're going to have to enter in 0.75 divided by 0.75 divided by, and then the square root of 8. So we hit the square root button, and then 8. Now this particular calculator follows the order of operations, also known by some of you as PEMDAS. So if you're using the Casio FX300MS solar-powered calculator, which I own no stock in, this is not a sponsored video, Casio doesn't even know I exist, you don't have to mess around with parentheses because this calculator knows the order of operations. So we go right to the times button, and then we type in 1.645. 1.645. And then we hit the equals button. And what we get, now the instructions said round to the nearest thousand. So what I like to do is I like to go point, and I put 3 little squares to remind myself that I have to do this to the nearest thousand, because we get this 0.936. .196, right? But I want to round this off properly. So this is 0.936. And, some stats professors, when they give long answer problems, they want it written. They want the answer written in standard, written English, if they're teaching in English, in the same language of the problem. So here would be the full credit answer if you have such a professor. For her observed mean to be significantly, I'm just going to write sig, greater than, and we go back to the problem, a half, 0.5, at the 5% significance level. Now I'm just going to write alpha equals 5%. Her mean, and this is a sample mean, but it's kind of obvious, observed sample. Her mean should be at least, and what did we get? We got 0.936. Now, what does this mean? I want to sort of ask you, because, sometimes, in fact, when I taught this, one of my students asked me, like, what does this 0.936 actually mean? So I want to go back to this idea. Suppose this researcher is doing an experiment and we want to know if the population mean is greater than a half. So a half is 0.5. So let's say the sample mean turns out to be 0.6. Well, 0.6 is mathematically greater than a half. But if you take chance into account, is it significantly greater than a half? It's pretty close. What about 0.7? Well, it's mathematically greater than a half, but is it significantly greater than a half? What about 0.8? It's mathematically greater than a half, but is it significantly greater than a half? When do we cross that line from being mathematically greater to being significantly greater? And the answer is when the sample mean is at least 0.936. We can lay claim to the fact that this sample mean is significantly, not mathematically, but significantly greater than a half at the 5% significance level. Now, here's a little question. Suppose your professor gave you the same exact question, might have been a little bit lazy and wanted to give you a second question and said, you know what? I'm just going to change the significance level from 5% to 1%. This way I don't have to, I'll just copy and paste. I'm not going to have to rewrite a whole question, but it is a whole different question. So the professor changes the 5% to a 1%. Right? So 1% is smaller than 5%. So here's my question. Is this going to be larger or is this going to be smaller? I think that's a really good question to end this video with, because if you have to do the calculation, your statistical intuition has not been formed fully on the stats 1 level. But if you're able to answer this question without going to the table and looking it up and plugging it in and finding it out, you're in a really good place understanding the concept of what statistical significance is and how dependent statistical significance is on the significance level. And with that, this is Dr. J. Lee Noose for College Statistics.